Greetings, everyone. This is Jeff Wilkerson, Professor of Physics at Luther College, bringing you the next in our series of what to look for in the night sky. We're talking about the week of July 7th this time around. So, the moon starts the week over 90% full, just over 90% full, waxes out to full, and wanes back to just barely under 90% full by the end of the week. So there is no week that we can have, really, that would be more moon obscured than this week. This is a tough observing week to see just about anything with that much moonlight splashing around the sky. But let's go give it a shot. We'll talk about some of the brighter things we can see, and let's do it. So the moon, during this time as the moon is doing this, it starts in Scorpius, moves to Sagittarius, Capricornus, and ends the week in Aquarius as it does all this waxing and waning. Venus, bright object in the morning sky, that's going to hold up to the moonlight, right? It rises sometime around 3 a.m. And so we have maybe an hour. You can see Venus much later than that. But we have maybe an hour where it's dark enough to see some of the things around Venus as well. And so, you know, we have this hour because on July 3rd, we were at aphelion. We were at our greatest distance from the sun, and we were moving about 29.3 kilometers per second in our orbit around the sun at that time. When we do an astronomy lab, we like to tell students we move 30, or an astronomy class at all, we like to tell students we move 30 kilometers per second around the sun. But because the Earth's orbit is elliptical, we move faster when we're closer to the sun in December, and we move slower when we're farther away from the sun in July. And so in December, we're moving about 30.3 kilometers per second. So there's about 1 kilometer per second difference in speed of the Earth when it's closer compared to when it's farther away. So there's a good trivia fact for you to share at your next party. So that's, we're moving slower. Because we're moving slower, we go less than our orbit in one rotation of the Earth. We have to over-rotate less to get the sun back to the same place in the sky, so that sunrise, for example, happens a little bit earlier than we're expecting around this time of year. And so we had our earliest sunset, even though we went through the solstice just a couple of weeks ago. We had our earliest sunset between 1 and 2 weeks earlier than that, or sunrise, excuse me, earlier than that. So we're gaining night in the morning. We're losing daylight in the morning. And it's starting to become noticeable. So pay attention to that as you're out there looking for Venus in the morning sky. On the morning of the 12th, it sits about a third of a degree. Venus is tracking to the east, this direction against the background stars as we have it drawn here. That's Aldebaran, is that bright star in Taurus, and that's the V of the Hyades that's there. We think of this as a fall-winter grouping of stars. So this is, to be looking for this in July, you got to look right before sunrise like this. But Venus is going to slide right above Epsilon Tauri right there. It's going to be hard with this being so close to the sunrise, but binoculars will help you out. Looking this late at night means the moon is still relatively far away and won't be washing that out, so you have a chance to see Epsilon Tauri there. So that's something to look for in the morning sky. Now in the evening sky, let's pay attention to Aquila the eagle, okay? So Aquila, we know there's the summer triangle. We've talked about the summer triangle before. You've got Vega, Deneb, and Altair. Altair is the southernmost star in the summer triangle, and it's part of this constellation of Aquila, and I've been caught many, many, many times saying it looks like a squished baseball diamond or a kite. And so there's the body of the kite, and there's the tail of the kite. And all of these are relatively bright stars, third magnitude stars that we're looking at right here. So they hold up pretty well to the moonlight. The moon's going to slide underneath this region. The moon's tracking east against the background stars too, of course. And it's going to be about 35 degrees south of Altair on the evening of the 10th. So that's about midweek, and it's going to be very, very close to full at that point. That's about as full as it gets right there. So it's washing this part of the sky out too, but these are bright enough stars. They should hold up if you have decent skies. So let's walk around this group a little bit. Right next to Altair. Altair looks like two dots of light. You've got the Gamma star. Altair is the alpha star in Aquila. You've got the Gamma star, 2.7 magnitude Tarazed. In the diamond shape here, you've got Zeta on this corner and Theta on this corner. Zeta is sometimes called Okab, and Theta is sometimes called Antinous in the Greek tradition, but it's also called Mizan from Arabic. As we've talked about many times before, Al translates as the from Arabic. And so we have Al Mizan. And so that translates as the scale beam. And that usually relates to all three stars, Delta, Eta, and Theta across there. So today we often just associate Al Mizan with Delta, a 3.4 magnitude star here at the base of that diamond. Between Delta and Theta lies Eta. Eta is about 40% of the way, I'd say, from Theta to Delta. Eta is a 3.9 magnitude star. Remember, the magnitude system counts backward. It's 2.5 times multiplicative factor in brightness for each step. So Theta is noticeably fainter than Delta and Theta and Zeta up here. And Eta we'll talk about Eta here in just a second. Let's go down to the tail of the kite. Lambda star, 3.4 magnitude star again, Al Thalamain. Sometimes it's called Al Thalamain prior, which means it's the leading, the westernmost getting across the sky, first Al Thalamain star. My understanding is that translates as the ostrich, and there are two of those. Eta Aquila is also called Al Thalamain, and that's why this is sometimes called Al Thalamain prior, to say it's one of the two ostriches. It's the leading ostrich going across the sky. Why those two stars, I have no idea. They're separated by a fair amount that share that same name, but it'd be an interesting project to try to figure that out at some point. So that's what we got with our bright stars. Should be a hold up to the moon. If you're not out on the 10th, if you're out a couple of days before the 10th and a couple of days past the 10th, let the moon clear this area just a little bit. It'll be a little bit better for you. But let's talk about these two stars in particular, Zeta and Eta. So Zeta is this third magnitude star, and it's a star that sometimes, if you look it up, it'll say it's a main sequence star, and sometimes it'll say it's a subgiant star. And we've talked about that this spring. One of the things we've talked about is stellar evolution sometimes this spring. If you plot brightness, luminosity, energy per time that the star is emitting as a function of temperature, increasing in that direction, we have this main sequence. Brighter stars or hotter stars or higher mass stars up here, lower mass stars, fainter stars, cooler stars down on this end. And those stars, what they have in common is they're fusing hydrogen into helium in the core of the star. When that hydrogen is all converted to helium, then something has to happen. And what happens is you start to fuse hydrogen into helium. You collapse a little bit, make the core hotter, and you start to fuse hydrogen into helium in a thin shell around that inert helium core, and you move off the main sequence and become a giant. And Okab, Zeta Aquilae, is right there. It's on that transition point, and so some people will call it a subgiant as it's starting to move up the giant branch, and some people will still call it a main sequence star, but it's right at the end of its main sequence life. We don't really know if it's still fusing hydrogen to helium in the core or not. So it's making that transition as it moves off there. It has a companion star that is 12th magnitude, and it's 7.2 arc seconds away from the third magnitude primary star. So that's the primary star we're talking about. The companion star is a red dwarf star. The companion star is a star that's down here on the main sequence, way down here at the low temperature, low luminosity end of the main sequence. So this star, 7.2 arc seconds, any telescope can separate, pretty much any telescopes and any observing conditions. 7.2 arc seconds should be relatively easy, but 12th magnitude is hard. 12th magnitude is a faint star, and my guess is you're probably going to need a 10-inch scope to be able to do this and to be able to see that star reliably next to the brighter companion. You might even want a bigger telescope than that. So that's our challenge object for this week, is to see if we can pull out that 12th magnitude companion. Just fun fact, the companion was discovered in 1878, so again, to be a little while ago, and it was 4.9 arc seconds separated the two then. So it's growing, and it's growing slowly enough. It's completed enough of its orbit. It hasn't changed its position angle. The two stars haven't changed relative to each other that much that we don't really know what the orbital period is. It's clearly hundreds of years, and so it's a long orbital period for these two stars. But if you got the chance, see if you can pull out that 12th magnitude companion. Again, I might not do it on the evening of the 10th when 12th magnitude stars are going to be hard to see in the glow of that moon. This whole week is going to be hard to see that. So if you don't get it done this week, you know where to go back next week to look at Zeta. Now over here at Eta, that lies between Theta and Delta right there, the Eta star, Eta Aquilae, is a relatively famous, well-known pulsating variable star. So sometimes stars pulsate when some of the pressure outward and gravitational pressure inward have a hard time finding equilibrium and staying there. And so that you'll get this pulsation in and out. And this is a pulsating star, and it's a particular class of pulsating star called a Cepheid variable star, which is the most famous class of variable stars that there is. Henrietta Leavitt, working in 1911 and 1912 at the Harvard Observatory, she was measuring pulsating stars. She was measuring variable stars in the Small Magellanic Cloud, a satellite galaxy to the Milky Way. So they were all the same distance from us, and that was magic, because if they're all the same distance from it, that means looks brighter is brighter. Okay, we look at most stars on the sky, and some look brighter and some look fainter. Some are intrinsically much brighter, emitting a lot more energy than others, but some are just farther away or closer, and we have a hard time pulling those two things apart. If you look at a group of stars that you know is together in space, and so you know the distance is the same for all of them, then you don't worry about that. You just say, if it looks brighter, it is more luminous. And so she was looking at those stars, and she was preparing a table for publication, and she ordered them in order of brightness. And what she discovered was that also turned out to be order of period of oscillation. So what the oscillating period, what the period of variability is, tells you how bright that star is intrinsically. And if you know how bright the star is intrinsically, and you know how bright it looks, you know how far away it is, forgetting for the moment about intervening dust and gas that scatters light out. But this becomes then, Cepheid variable stars become then one of the most important distance measuring tools in the universe to help us see distances in our galaxy and then distances to relatively nearby galaxies. And so this is a key linchpin in the cosmic distance scale. And this is a Cepheid variable star, and it's a Cepheid variable star that, if I remember correctly, goes from about 3.5 magnitude to 4.4 magnitude. That number's somewhere in the middle there. And again, that's a factor of 2 in brightness. That's more than a factor of 2 in brightness. So it's 2 times fainter at its faintest than it is at its brightest. And so you can see this. And this is a good naked eye star. You can just go out and look at this and see it. But if you want to take a picture of this every night for a couple of weeks, you should be able to see this star getting dimmer and brighter and dimmer and brighter, because it has a 7.167 day period, a well-known, solid, well-established oscillation period. And so you see this 7.167 days. So in a week, it goes from brightest to dimmest back to brightest again. So within a few days, you see it going brightest to dimmest. And so all you need is 3 or 4 or 5 clear days in a row. Now, again, the moonlight doesn't help you here, because it's hard to measure the brightness of a star. It's hard to see the stars in the moonlight. But if you're out there taking pictures of the night sky, why not? Take a picture of Eta and some of the surrounding stars over the course. If you take a picture of the whole of this asterism of Aquila, you're going to be able to measure the brightness of Eta against some of these nearby stars like Delta and Theta, and you're going to be able to see it. You're going to see at its brightest, it's going to be about the same as Delta. And as its faintest, it's going to be much, much less bright. It's going to be about half as bright as Delta. So that should be a fun thing to do, a project. When you get a chance to take a picture of this region of the sky, or just go out and observe and sketch and write notes for a week or two, you can watch this star getting brighter and dimmer and think about Henrietta Leavitt and her work at the Harvard Observatory over a century ago now, and it helped us anchor the size scale of the universe and understand how big the universe is. So that's what we got for you this week. Tough moon week. Venus is interesting in the morning. Got a little bit of work we can do there. We're going to look at Aquila. There's so much other stuff going on here. Next week, when the moon is cleared out, we'll come right back here and look at some other things near this part of the sky. We may spend a few weeks poking around Aquila. It's a great time of year to be observing it if the moon's not there. But we started with a Cepheid variable star and a really, really tough binary star to pick out there. But we can just also start to learn all of the stars of that grouping, of that constellation, that asterism. That's what we got for you. That's our week. As always, everyone, thanks for watching, and we hope you have a great observing week ahead.